Welcome, colleagues, to SAMPI's Technical Committee webinar on toward a new methodology for design and failure analysis of PSA bonded joints, delivered by Dr. Michael Larson, and actually our own Felix Chen is also a co-author. But welcome to the webinar. Please go ahead and in the chat, enter in your name, your title, your company name, and your geographic location. So I'll pass it over to Dr. Chen very soon, but please go ahead in the chat. Do a self-introduction. Welcome to the SAMPI Technical Committee webinar toward a new methodology for design and failure analysis of PSA bonded joints. So again, please go ahead and enter in your chat your name, your title, your organization, and your geographic location. Thank you. Felix, I'll pass it over to you, and we'll probably begin in a few minutes.
Okay, I will just repeat in the chat there. Please enter, as Raj said, your name, title, company name, and where you are geographically. And there will be a question period at the end, and you can enter your questions in the box. As you can see here from the title slide, there are numbers on the slide. So it would help, Michael, if you put the slide number you're referencing, if you have a question pertaining to a particular item on some slide. So Raj, let's maybe give it, what, 2 more minutes, 3 more minutes?
Yeah, I think that's fair.
After-ish.
We'll give it a few minutes just to let everyone join. Yep.
Okay. Okay, let's start then. My name's Felix Chen, and I am the chair of the Bonding and Joining Committee of SAMPI. I got my PhD in Material Science and Engineering at UCLA, and I am currently a reliability and quality engineer at Chimeta Corporation in Redmond, Washington. We make a satellite internet antenna that's, I like to call it an upscale version of Starlink, because that's really what it is. And I want to introduce our speaker, Professor Michael Larson. He is a dear friend of mine, and we met about 25-ish years ago when I was at TRW Space and Electronics, and Michael was a visiting scientist. Michael got his PhD in mechanical engineering from MIT, and he joined later the University of Colorado Springs' mechanical engineering department as the L. Pomar Chair of Engineering and Innovation. And it pleases me to say that when he was applying for that, I submitted one of the recommendations for that, and his dean called me to chat about it further, and I just lavished superlatives upon Michael. He did structural analysis. Prior to that, he did structural analysis for the Air Force, and he has founded 4 startups in medical devices. And this is some work that Michael and I did 2 years ago, and we're still continuing on and off. And one day we'll really get into some of the meat. But anyway, as I said, if you have a question, please put it in the chat. And if you could reference the slide number, if you are asking about a particular item there, that would be very helpful. So Michael, you want to go ahead and go for it?
I do. Thanks for that kind introduction. And just to be clear, was I supposed to send you some percentage of my paycheck every month? I'm sorry, I missed.
Oh, that's not supposed to be made public, but thanks anyway.
Well, welcome everyone. And as Felix said, we are talking today about some work headed toward developing a sample that will be particularly useful, I think, when thinking about incorporating PSAs, pressure-sensitive adhesives, into our designs. And I have enjoyed collaborating with Felix. He certainly has the mind of a scientist. I like that he is very fastidious when it comes to trying to make sure that we understand all of the aspects of a problem. And for me, he brings a material science view that I appreciate a lot as a mechanical engineer. And certainly today's work covers both of those domains. So it was nice to work with him on that. And this work did spring from some problems that were very practical, but very important in Felix's work. And I say hats off to Chimeta for wanting to share with the community about some of the insights and some of the solutions to problems to share with the community as a service. So with that, first I always stress to my students to avoid the tunnel vision that often comes when solving problems. around structural mechanics, that we don't get focused on one particular aspect and forget what could be a more sensible solution some other way. And that was an issue that did come up in this particular solution. So be on your guard against tunnel vision, knowing that in general, when we have a mechanical failure to deal with, we can address that typically in one of three ways. One would be changing the loading or the service environment. Just load something more gently and it's more likely to live. This is one, though, is rarely a valid solution because we're designing something for a particular service environment. So then we turn our attention to changing the materials, and those familiar with the material selection methodologies, we want to eliminate as many different materials as we can. If there's no reason to have a different material, then don't stick with one. And if we have to use a material and it's failing, well, can you make it stronger? Can you make it better? Can you choose one? If we're doing a one-off prototype, usually choosing the Cadillac option is possible. If we're mass producing things, however, pennies count, and we really need to know what is that boundary between what is the usually cheapest, lightest, best material that just meets our needs, so we're not wasting resources. And then the third option available to us is just changing the overall geometry in order to change the distribution of stress strain or whatever it is that is causing the failure. So it isn't about necessarily changing the materials. In this particular case, we're talking about an adhesive that we might use, but we're talking about rerouting the distribution of loads to be more gentle. Removing stress concentrations would be the obvious thing. So here we had an eye toward number two, looking at a selection process for material, and for a particular application, it became evident that if we were just attentive to changing geometry, we could get something out of that. So more later. So during today's talk, I'd like just to introduce those who haven't been using PSAs to join structural components together. Just very briefly, they're useful, convenient, and they are a little different than other adhesive or mechanically fastened ways that are available to us. And then when peeling's not appealing, we're talking a little bit about peel tests, which typically is the standard for judging how strong or useful a particular adhesive is, and why that might not be the best measure for these class of adhesives. And then a little justification for borrowing fracture methods. Fracture mechanics is an area I've done a lot of work, and it is interesting that a lot of people want to grab ideas and run with them, but there are limitations in adhesive domain. And then we're going to revisit that notion of changing some geometry in a simple but ubiquitous sort of application. And then finally, the groundwork for this super layer approach to novel testing that will help us to really get at the heart of how we can do a straightforward test ourselves that replicates the important features of a problem for choosing a PSA that would be good. So pressure sensitive adhesives, in general, we contrast these with structural adhesives. And like every adhesive, we can have failures that happen at the interface between the adhesive and the surfaces that they are bonding, or we can have failures inside. However, the nature of a failure inside the adhesive tends to be much different for this class of adhesives. And the nature of that bonding to the surface is different. Most notably, it tends to be much weaker. And so it is something of ironic that we get a strong adhesive bond out of something that often seems to have very low work associated with debonding the surface contact. So how do we define them then? These form a bond on contact without needing water, solvent, or heat to activate. So this is not a two-part thing like an epoxy. They can be repositionable or permanent, depending on their formulation. And they can adhere to a wide range of materials and surface roughness, typically as long as we can get complete wetting of the surface in order to take advantage of the PSA's capability. The three most common that we use in design structural applications are acrylic. These tend to be durable and tolerant to environmental factors. Rubber-based, and these typically give us an initial tack that is very strong, but less resistant when it comes to heat and aging. A lot of early internal components, the interior of automobiles used rubber-based ones that turned out to not hold up over time. And then finally, silicon, which is usually classed as more custom made, but this is where performance is critical, typically, especially high performance. They tend to be the more expensive of the lot. And I just grabbed at random. I have no connection with 3M or any interest with them. It just so happens that they do a pretty good job of making some high performance PSAs. And so I grabbed tape. There was a little picture in the previous one. If we look at the standard technical data sheet, just something I like to point out is the adhesive thickness for these tapes tend to be very small. We're talking 0.04 millimeters, 1.6 mil. And this turns out to be consequential when it comes to modeling these interfaces, because often we do trap this very complicated material in a very small zone compared to the environment that the failure is going to happen. And I think that works in our favor when we're thinking about a standard way of approaching our failure analysis, and certainly plays into the justification for using a fracture kind of approach for modeling these things. The other point on their 12-page technical data sheet is all the information that they give us concerning mechanical performance is a 90-degree peel test. And here, just the first one with a particular set of parameters for relative humidity and temperature, 4.4 newtons per centimeter. And that would be the relative to the width of the tape that we're using as a measure. And it's always easy to poke holes in other things and what people do. And the peel test has for a long time proven, I think, to be a good measure for judging in a relative sense whether one adhesive is stronger than another. However, and I have a photo to show, the peel test kind of falls down for us when it comes to pressure-sensitive adhesives in a lot of our very practical applications. Again, those where the components being bonded are generally still in a linear elastic regime. The ASTM standard that is referenced there, that is commonly used for peel adhesion of pressure-sensitive tapes in particular, the working group that developed this standard in the standard itself, of course, tells us that the difference between two single observations should not exceed 20% of the average of two observations in 95 out of 100 cases, blah, blah, blah. There is a lot of variation in peel test results. And if you look at a large lot and you're trying to do everything the same, you typically, well, I have seen lots of variation in the actual test results. As a consequence, people have done a lot to try to modify particular peel tests to give information that may be more germane to a particular output. thanks to Michael Bartlett, whom I don't know, who categorized these things in a material science paper. And you can see we've got the 0 peel, 90 peel at 90 degrees, 180 degrees T's in order to try to get rid of substrate dependence, and lots of options here, some standardized, some not. And I would submit, though, that none of these perhaps are what we want to use for a typical PSA application, because the limitations here for peel tests include things like complex stress distributions, which those of you who have done analyses here, it is pretty complicated what's going on at the leading edge of a failure for bonds. Substrate dependency, so we standardize these in peel tests, but that can look nothing like the actual materials that we're trying to bond together. Rate sensitivity plays a role. It's hard to get a peel test at one rate and sensibly apply that to a different rate that we would have in service. Environmental factors. The mode of failure is a single mode typically for peel tests. We usually have multi-mode failure going on in real situations. Our sample preparation goes a long way to adding to that statistical distribution. Directional effects for our adhesive, and the nature of the substrates. The one, though, that really rears its head when we think about pressure-sensitive adhesives is this energy dissipation mechanism, which is what makes this class so valuable, but I would say why it's so difficult to accurately model. And what we find here at work in these PSAs that are holding two surfaces together, we can have adhesive failures where we see interfacial debonding, the adhesive separating from the surface. This traditionally looks at the relative surface energies of the two surfaces involved. Cohesive failure, when our adhesive is failing itself, coming away, there's bulk deformation of flow, large strain kind of deformations. There are varying thermal dissipations associated with that work of failure, tackiness, surface wetting, adhesive toughening. We find people are beginning to add things into the adhesive in order to give some kind of analogy to the fracture world, an R curve kind of behavior, something that Dr. Chen did a lot of work with in the past. There's time-dependent creep behavior. So there's viscoelastic and viscoplastic things going on in this. And it's this last one, the viscoelastic deformation, that really is the twist that can work for us a lot. And if we don't account for it properly, we'll miss the boat in choosing the right adhesive. Here is a picture that there are lots of papers out there that show similar sorts of things, but this is a 90-degree peel test, much like is the standard when people are giving us data sheets for their PSA products, showing the massive amount of deformation that you see these ligaments or fibrils that are stretching between the substrate along the bottom of this figure and the material that is adhered, that is peeling upward. Just a lot of deformation. And it's interesting, the material is prepared to give us this kind of resistance in a process zone area, but it's in many instances the fact that we have a bulk material that we're adhering, we don't see this kind of gross deformation and strain surrounding the substrate. So there's a lot to be learned by this, and certainly if you're adhering a thin film, then this very large deformation comes into play, a lot of nonlinear behavior. I would submit that in many cases, the domain, the parts we're adhering aren't going to permit that extensive deformation. Yet remember, the material is still providing the capability, and that's why we get a lot of dissipation going on non-linearly. And in the reference to Richard Villey, who did us a service of publishing this work, it's in the International Journal of Fracture. And again, I would say that traditionally, if you look at the history of fracture mechanics, this is not a fracture problem, but it has become commonplace in the adhesive world to apply fracture theory and approaches to the degradation and failure of adhesives. And is that okay? And I think yes, I think it is a sensible thing, even if maybe it doesn't look like a traditional definition of fracture. A recap of how fracture mechanics got to the state it's in now. At first, it was in the domain of material scientists to try to tell us how to predict and model fractures. And of course, going back to Griffith cracks long ago, it seemed to make sense from a thermodynamic point of view to ask, is there sufficient strain energy in a system to provide the energy needed to create new surfaces? And if so, then those new surfaces or crack will grow and appear. Unfortunately, it isn't practical to determine what that amount is. We can get surface tension values from very well understood experiments, but in practice, there's a lot more going on than just the generation of new surfaces, even in what we would call ideally brittle materials. So although a very nice notion, it wasn't something that provided a lot of practical use. It then ended up in the hands of the mechanicians, the mechanical engineers, and linear elastic fracture mechanics was born when we had people like Westergaard and others that were able to identify what the stress field around the singularity of a crack tip looks like. And with this universal solution, we observed that it's scaled with a single parameter that we call the stress intensity factor. So the stress intensity factor doesn't give us the stress at a crack tip, since that's always infinite, but it does scale how quickly one gets to infinity is a way of thinking about that parameter. And having done real stress analysis, I was shocked at how people took that very simple yet powerful concept, but then start applying it everywhere, even when it didn't strictly apply. And as a consequence, we have had, last count, I think it was a gazillion ways of modifying that basic solution found for small scale yielding conditions. And it's been used liberally, as I say on the slide, with modifying features galore. With our particular application looking ahead of pressure sensitive adhesives between two elastic surfaces, the most common way I find people are tackling that is with a process zone where we actually represent some closing forces on the crack tip, a pseudo crack tip, and then these represent the effect of the adhesive that is pulling the surfaces together. I have yet to find a deterministic, though, application of that. It usually turns out to be a curve fitting exercise where we do one in order to find out what function defines those closing tractions, and it is difficult to use. So again, I admire people who have been working in all of these fields and doing us a service for enhancing our understanding, but I do think we need something better for giving us something practical and useful for judging the quality of these interfaces. And as they say, nothing is new under the sun. That crack closure process zone goes all the way back to Barenblatt and Dugdale back in the day for trying to account for plasticity in metals and non-linear things. The final bullet says merging of the two approaches is where we are today, because we now use the computational approach, usually finite elements that the mechanicians have given us, but we are back to using the engineering principles in order to characterize critical failure of cracks, or in this case, adhesives. And I think these are the tools that we need. So I thought it worth, for those who haven't done a lot in fracture mechanics, thinking about when things apply and don't apply. We do appeal to this idea of small scale yielding, and this on interfaces is something that has been covered by lots of the giants in the development of fracture mechanics. And here is a figure that I lifted that is royalty free, but well, the reference, you can find it there. But I thought it was a nice figure from someone's dissertation about reminding us what we mean by this. And in the legend, showing areas around a crack tip that correspond to a large strain region, a J-dominated zone, a K-dominated zone, and then a no single parameter description. And in that lower left cartoon, we see a crack where the dark large strain region, and here you can think for a bulk material, plasticity is a great mechanism to be thinking about. It's the plastic deformation that in practice kills the stress singularity at the crack tip. So nature abhors a singularity, except maybe the Big Bang, but that's for a different lecture. Nature abhors a singularity. What gets rid of it here? It's the nonlinear plastic deformation. So there are no infinite stresses, but there is a zone outside of that where the stresses match very well that classical solution for the singular stress field. So since that is the case, we can imagine cutting out a zone around this crack tip and putting boundary conditions on that cut surface that replicate the known stress distribution from the singular solution scaled by K. Hence, we have a sample that we can test according to an ASTM standard for getting stress intensity factors, a test that we can assign a critical value, the fracture toughness, to a material, and then use that as long as the cracks aren't causing nonlinear zones to intrude on some boundary that is well defined by our known solution. And in the upper right corner here, back in the 60s, John Hutchinson and Jim Rice at Harvard developed an HRR solution that actually described the stress field a little outside of that zone where we could extend our modeling and understanding. And usually it's the J integral, a path independent integral where we can compute the energy around a crack tip and do that in a zone even where there is some nonlinear mechanisms at play. And we, in fact, in the analysis to come, will employ the J integral for that purpose. The lower right, though, shows us a place where linear elastic fracture mechanics doesn't work and HRR doesn't work. Yet I find people all too often using fracture mechanics sorts of approaches for those, and it's unfortunate, but I don't know if we can do anything about it or not. So a survey of the current analysis approaches for doing PSAs in particular to account for this very complex nonlinear mechanism that's going on, mechanisms. There's viscoelastic modeling. People are applying Maxwell, Kelvin, Voigt, dashpot, springs, dampers, Prony series in mathematics to try to assess that. These cohesive zone models that I mentioned, where we have a set of pseudo loads to replicate what's happening by our adhesive. These are called traction separation laws. I put the quotes. Usually the laws don't have quotes. They're not laws. They're usually got from an experiment, and then we infer something, and it's a case-by-case basis. People have employed nonlinear finite element analysis, which, depending upon which code you're using, can involve a lot of ill-defined constants that a user would have to employ. Molecular dynamic simulations for basic idea of what's going on. These tend to not be very easy to apply when it comes to choosing a proper adhesive. Multi-scale approaches where we combine these things. And then, of course, the latest trend is machine learning. And I find these being stuck in a lot of academic proposals in large part because that's the hot area. Machine learning, though, is often only as good as the cases that we're putting in, and we kind of know ahead of time what the answer is going to be because we're selecting the cases. So we need to have a jaundiced eye toward how people are employing machine learning in all aspects of mechanics modeling. So while these are many interesting academic exercises, a few of them, I think, are at a place that provide us with good guidance for how we're going to select an adhesive. So now, thinking about fracture mechanics being applied to candidate models of how delamination of adhesive surfaces with PSAs would look, we have edge delaminations proceeding from an edge. We can have an area between two surfaces bounded around a periphery that is separating. And we have buckling that is something of a distinct situation than that mixed mode interface crack. The buckling tends to be very much an opening mode sort of thing, whereas the mixed mode interface crack has a strong preference to shear, but there is some opening tendency. But it's the mixed mode crack at the top that is, I think, most representative of how typical failures occur proceeding from an edge. So if we put this in a specific context and think about two bulk or three bulk layered materials, and we're going to be adhering these with PSA layers, and I think for PSAs, thinking in terms of plastic materials, the polyethylenes, polypropylenes of the world that are finding more and more applications is the sorts of materials that lots of people are looking to join with PSAs, and challenges because those, particularly polyethylene, notorious for having a very low surface energy of adhesion, and PSAs are showing they can be a good solution. So we have this, and just for giving us some insights, it's symmetrical about the center. This is pretty easy to develop a simplified analytical model to get our head around what's going on. We can assume that we're going to drive a delamination by having a temperature change here where P1 and P2 have two different coefficients of thermal expansion that is going to drive this, opposed by some shear on the interface, so some just simple representations turns into this governing equation for the distribution of shear to satisfy equilibrium. And then using some typical materials that might be a stiff plastic with a much more compliant middle layer with PSAs in between, lifting some typical material properties for the thermal expansion, the modulus, thicknesses of these things. What we see is, not unexpectedly, is this is a distribution of the interfacial shear that's symmetrical with the center of the layup that is intense at that edge, which is why we typically see delaminations proceeding from an edge of these kinds of differential temperature driven failures. And this happens to be just some numbers for a delta T of 85 degrees C, with numbers representing, again, structural plastics that we often want to glue together. So the nice thing is it's intense at the edge, but it's fairly small. So we can engulf that zone into a process zone that I believe we can characterize a boundary with our J integral domain that will capture what's going on. And then as the delamination proceeds, we'll see in a minute, it proceeds in a very self-similar sort of manner, continuing that justification. This is where I mentioned at the beginning that although the focus is choosing the right adhesive, seeing that massive shear at the edge told us that maybe we could look at a change in geometry that might help limit the onset of failure. So what about a simple chamfering strategy of just chamfering the two layers top and bottom? What does that do with changing the material? And a simple finite element model of looking at a chamfered surface and not with that same delta T being applied. In this particular case, it was like a 90% decrease in the amount of strain energy in that sensitive domain of intense shear to be available for delamination, and the energy needed to take the adhesive apart. So clearly there is something to be gained here by just a simple geometry change if your application will permit. So if you're seeing a lot of edge failures with adhesives, if you can think about some way of just killing the available stress by making the edge more compliant, that works. We thought this warranted a closer look. So we actually did a detailed ANSYS finite element model for, again, the same types of a stiff and a compliant plastic being bonded together in layers. On the right is the inset of a detail of where a crack, which I say crack, and of course I mean a delamination leading edge appears. And we're going to use the J integral to take multiple contours around that tip to look at the amount of energy available for extending a delamination. And here are some figures out of Abacus showing a magnified deformation for the hot side of that temperature change. And so in this case, what we have is the top part is expanding and making life difficult for that leading edge of the delamination. And in the bottom, with the chamfered edge, making it less likely to grow that delamination. This is for the carved in 4 millimeter delamination from the edge, looking at particular values of the energy available for driving the crack. Again, much less And here is where I mentioned the self-similar nature. Once you get a long enough delamination, you get pictures looking like this, where this is the von Mises component equivalent stress in a geometry. And once you get away from either the chamfer or away from the edge, because of the ratio of the length in the horizontal direction much bigger than the dimension vertically, you end up with a self-similar sort of growth that as this delamination proceeds, this field looks the same. So this lends it to a classic technique of fracture mechanics for estimating an energy release rate by looking at an area downstream from the delamination where you have no stored strain energy in these two layers, top and bottom, compared to the energy stored in an equivalent slice far upstream from the area of interest. And you can easily represent that strain energy that's being driven by the difference in thermal expansion coefficients. And so as the crack changes by that increment, we know what the energy release rate is, and it proceeds at a constant rate, something that is often seen in these edge delaminations in the fracture world, where we have bonded interfaces and interface cracks. You don't have to get very far in before you end up with a self-similar kind of situation for extension that allows us to have an upper bound on what the critical value of the J energy release rate is. Something else we found that was kind of interesting around this chamfering is looking at the chamfered and unchamfered, which are shown in the center of this figure, with plots above the mode mixity, and that refers to the relative proportion of how much is shear versus how much is tending to open the crack, which are different for the chamfered and unchamfered cases significantly. So we're changing the failure mode. So something to be aware of is if you do chamfer, you are using an adhesive that then is subject to, in the cold side of the thermal cycling, subject to a different sort of mode loading than if you're not chamfering, which again, not unexpected, but at least you can get some idea. And then in the bottom is what is the J integral value for these? And it is interesting for very small delaminations, something that you would miss in manufacturing and production in your inspection, perhaps, that in the lower left, we see we do kill the driving force for very small initial, say, inclusions that might be there, insufficient bonding that can occur at those edges because of particles or maybe oil, that you can actually inhibit the development of these failures at the edge by judiciously doing that. Moving on then, thinking about how best to characterize in a way that represents the actual loading that you see for pressure sensitive adhesives, how about some other tests that we might look at? We did our own testing with some double lap shear, which is a special case of a peel test of a 0 degree. And since in general, these things are primarily driven by shear in a temperature application, again, it's bulk materials in their linear regime, not the 90 degree peel by any chance, this would seem to be intuitive. But pulling these things apart, we found specimens to be unstable, different initiation sites. So we thought we would be creative and apply a special kind of test but that is primarily mode 1, the dual compression double cantilever specimen, and found again that this was highly sensitive for us as we changed geometries slightly. We were getting lots of issues to account for that didn't seem to be the direction we really wanted to go to get the material properties of a PSA relevant to our problems. And that's when we hit upon this notion of using a super layer in order to impose a, thanks for the spell checker, delaminating is not a word that my software likes, and it changes it to all sorts of things. I just realized it changed it to debunking energy here. That's delamination energy. Usually it changed it to delimiting, but I'm glad it fixed that. So I'm sorry. To impose a known energy to drive a crack, we thought of a super layer, and this was something suggested to us by John Hutchinson at Harvard I mentioned before, because this is a technique often used in the area of thin film metal coatings in order to try to get at the delamination levels for those types of structures. There's no reason we can't apply it to the notion of getting a known and uniform stress distribution to drive the delamination, so we can have a specimen that allows us to unambiguously try to pinpoint a useful value for using in the analysis, much like our analogy to a stress intensity factor exceeding the fracture toughness. Here we want to work toward a factor characterizing the interface that we can compare to a known value. So the super layer is, in this case, we've bonded the lower two white colored layers, and we're slapping a much stiffer material on the top in order to be the driving source for the delamination to occur. And we tried a number of different specimens with and without a chamfer. So here are two specimens that we prepared with a similar and just a Sharpie marked delamination that we put in ahead of time, where the PSA is not bonded between that lower white level layer and then this middle layer. These specimens we used, the super layer is the same stiffness as the substrate material, thinking about that as a way of simplifying the analysis. And with a number of these specimens that we made and put in an oven and then registered the temperature at which we observed delamination spontaneously occurring, because if you put these specimens in an oven, either cool them down, they'll reach a critical value where the two pieces will come apart. If you put it in a hot oven and heat it up and monitor them, you reach a temperature where the PSA layer fails, and it fails all the way across. We did some modeling with this, and just because we are enamored with this idea of changing the geometry in order to try to preserve our specimen, here's an example of having a 10 millimeter long failure in a specimen that you could see is about 40 millimeters tall in a layer that picks up a PSA adhesive. Just having that chamfer out there lowered the driving energy release rate, having the chamfer significantly. So again, if you have some initial flaw in your adhesive layer, it happens to be at the edge where you have the stress concentrations, you can reduce the driving force with a geometry change solution that will help. So that is, again, something to keep in mind rather than always just to search for a better adhesive. maybe you can do something to make the adhesive happier, more accommodated. When we put the chamfer in a specimen without an initial flaw, as best we could tell, by the finite element model, the maximum stress remained at the surface of the non-chamfered one. With our chamfer, though, the maximum stress actually moved to a place interior to the specimen. So just on a traditional failure mode that you would base on a maximum stress, we were able to move that location. So try to wrap this up and where we stand on the development of this new sort of specimen. And Felix and I welcome your input, whatever it may be, for a particular specimen. And the idea is you would build something that replicates the actual product, the actual structure that you're looking to put together. You can do that activity of looking at what is the failure level as you heat and cool your specimen. And the curve on the right is the design curve that goes along with that. You do have that shift of the mode mix, whether you're on the hot side of things or the cold side, where we get that jump from a more balanced shear and opening to more on the driving shear, dominating things. But the blue line shows the J value at different temperatures. So once you in an oven, you can identify what the critical value is for where the failure occurs. And then you can get a sense of, for temperatures less than that, how close are you, what kind of factor of safety are you dealing with within the bounds that cause failure to occur. And we further did some testing with that particular specimen, and we tried a whole host of materials. And one thing we found is these days people are finding that non-continuum granular materials are finding more and more applications, because these can be tailored by changing the density, by changing sintering pressures, temperatures when manufacturing, that we can get functionally graded materials that can be compliant where we need compliance, say at the edge of our structures, and be more consolidated and stronger, stiffer in other places. And when we did some experiments with some of these more particulate materials that are held together with structures, we've got a little video here to show that we created a hat specimen to drive things in a mixed mode way, not unlike our specimen, and pulled on it. So this is what the specimen looks like. We've got a PSA in between some layers. You put this in a test frame and pulled on it, and then with a high-powered microscope, looked at the leading edge of the delamination or debond. So in this picture on the right, the particulate layer is not bonded to the lower substrate. On the left of that arrow, it is bonded, and the specimen is pulled apart at a rate of 500 microstrain per second. There's a little blue indicator showing these particles are about a quarter millimeter, but you couldn't really see what was going on. Can I pause this video with clicking on it? Couldn't really see what was going on in the actual video. In fact, by eye, it was hard to see that anything was moving. So to stress the fact, just what follows is scrubbing the video forward, back at a high rate. You see there is a lot of deformation that gets induced between the substrate through our PSA without the PSA letting loose, as we say. But as that red box showed, there was an interesting failure that ensued that wasn't expected of the particles making up the material actually rolling along the interface. So not that we're particularly interested in this for things that lend themselves to a continuum model. If we tried to do that with this sort of material, I think we would miss the boat because of a much different failure mode. And even after this much deformation with particles rolling, the two parts were still hanging together with the PSA. So we just offer that as food for thought tacked on the end. And again, I think the study of granular materials and looking at ligaments holding the constituents together is important. So I think, Nikki, sorry to see you go, but it's nice to meet another Larson. I don't know if we're related. Thanks for tuning in. Well, Felix, that's what I have. If you want to moderate some questions, I'm happy to.
Yeah, we have a few. So we have 4 minutes left, but that's okay. We don't have that many questions. So the first one on chart 4 for acrylics. Quoting, I've had good success with waiting about 24 hours to achieve full adhesion. Is this something you are familiar with? Meaning why the 24 hours?
That is a great question. And it's that old joke where I'm going to direct the questions to my chauffeur in the back of the room. Felix has actually had a lot of experience with the practical aspect of using adhesives, both PSAs and liquids. And from his experience, speaking for him as a lead-in, they did see some issues related to the importance of surface preparation, but also allowing for cure time before adding any structural load. So Felix, anything you can comment on regarding that?
I'll mention one of the things that you want is a certain amount of entanglement because that helps with the dissipation of your stress concentrations away from the interfaces. And another is the surface prep that Michael mentioned. A lot of the mechanisms there are points where you create more entanglement. So the longer you wait, you create an optimal amount of entanglement points. That's how some of the surface treatments work. So that would be, I would guess that's the reason for the 24 hours. And then
different. Oh, go ahead. So I was going to say different manufacturers have different guidelines they recommend. And of course, they talk about sufficient surface preparation. So with some of these PSAs, the manufacturers will say things like, keep it under elevated temperature for 3 hours, something like that. If you're not adding heat, then you can still let them sit, but for an extended time. And I think your 24 hours would seem reasonable to correspond to a few hours at an elevated temperature.
And then second question, great presentation. Is it possible to correlate the nonlinear deformation that you showed from the International Journal of Fracture to durability of the composite? Michael, you remember which slide? I remember you showed that International Journal of Fracture figure.
Yeah, that was that, no, sorry for the time it takes to go through these. So just looking at the wild picture of, I love the fact that these ligaments are so long with these PSAs, giving you some closing traction, even as, of course, it's diminishing as these are stretching. And so what was the question about this?
So can you correlate the nonlinear deformation to durability of the composite? Or of a lot of the audience is composite. That's the question.
Okay. Well, I do think that this sort of thing can help with durability to act as something of a mechanical fuse. So if your structure overall is going to be limited in the maximum amount of deformation, the maximum strain in the vicinity, that something else is going to be assuming some of the load being shed by the failing interface. Because presumably, if you have a load-driven thing, this is an unstable situation. There is no durability. It is going to fail. But if you have a deformation-controlled situation where other things are going to take up the slack, then certainly this will help with durability, because it will still give you some load capacity over time, although, as I say, greatly diminished. And I wouldn't count on it for the long haul, because as we mentioned, there is viscoplastic deformation also occurring. So this is not an elastic effect over the long run. And within a matter of, minutes to hours, you're going to lose that benefit of some closing traction in this vicinity.
Okay, and then thanks. The final question, how realistic is or did you use 1 GPA for the PSA in your FEA model, and how realistic is that?
It was within the domain of what the vendors that we were talking to were including in their upper end high performance PSAs. So of course, PSAs run the gamut. Arguably, you could say masking tape can qualify, and certainly not going to characterize a lot of tapes, but
Okay.
we did find some that indeed was not out of the realm of realistic.
Okay, I think that wraps it up. Raj, any final words?
That's it. No, thank you, Michael. Thank you, Felix. I think we're going to have a short survey right after this. So please stay tuned. And then the next webinar, we do these on a monthly basis. So the next webinar will be the third Wednesday of October. I believe that is
That the Ocean Gate one?
October 16th, it could be. But please watch out for that. So thank you, everyone, for attending. And we look forward to seeing you again. Thank you again, Michael and Felix.
All right,
I
thanks,
enjoyed it.
everybody.
Thank you.